didn't hear, I might have missed a discussion about building comfort, especially in very tall buildings with residential on top, and standards for comfort and motion. We're doing a building in San Francisco, and it's got residential on the top, mixed-use tower, and the comfort level of the damping in wind circumstances seems to be a ruling criteria over and above the seismic.
Often, just sort of as we touched on, often at sort of very slender, tall buildings, some of the governing criteria for the building stiffness may be driven by building motion criteria. And essentially what that is the CTBUH, the wind consultant, and ISO have a number of sort of typical standards, and there are 3 criteria. So the first is a 1 in 1 year acceleration limit, and it's frequency dependent, so that value will fluctuate a bit depending on the building frequencies in the primary modes of vibration. The second criteria is a 1 in 10 year acceleration. So the 1 in 1 year and the 1 in 10 are basically accelerations that you'll feel, and the sort of standards have been codified just based on perception studies where they put people in situations where they feel these accelerations, and there's been a sort of agreed upon industry value that the majority of the people that may experience these motions wouldn't feel uncomfortable. So the 1 in 10 year limit for residential building is about 18 milli-G, and for a commercial job, actually there's a higher limit just because you're not laying in bed. It's not as frequent as an occupancy as a residential building would be. And then the third criteria is a torsional velocity criteria, which is basically if you were to look at a fixed object, you'd see something rotating on the horizon. And then essentially what we're striving to do in all cases is to meet those 3 key criteria. And basically in all of these projects where you have a tall, slender structure, we're all essentially trying to strive to hit the same benchmark. And then, essentially at these heights, it just becomes impractical to throw stiffness at the problem because the walls get too big, the lateral system gets too bulky, and that's where the damper comes in handy, because it's a very efficient, and there are various configurations of dampers, but they're very efficient at handling these motions. So I hope that answers your question. Our 1 year limit?
Yes.
It came out to be about 9.5 milli-G, I think. Our first mode period was about 6.5 seconds.
And what are you using for the torsional velocity criteria?
It's 3. We were marginally over it. I think we came to 3.1, but one of the strengths of working with RWDI is they've done additional human comfort studies. So their internal check in that sort of gray area around 3, they've done a lot of additional human comfort studies. So they're comfortable sort of in and around that range. So we're a tiny little bit over 3.
And then a question for Hezi. I notice your liquid damper is offset from the center of stiffness of the building. How do you accommodate that in the wind tunnel testing?
Well, the RWDI provided the location of the damper and the size of the damper. We gave them where they can accommodate it. The reason they couldn't center it on the center of the core is because you have elevators that have to go up to the bulkhead.
This is another question for Hezi. The slosh damper is very interesting. How did you validate its performance to give you the damping criteria that you did in your sensitivity study? How did you validate that it was actually going to perform the way you wanted it to? What kind of analysis did you do?
Again, we receive the information from the wind tunnel test. It's sort of like they provide us the service of designing the damper. We did not design the dampers. We're not designing dampers.
So they gave you the size. And
they gave us the size.
And
they gave us the damping ratios and the accelerations.
all right, and that was RWDI.
Yep.
Okay, thank you.
This is another question for Mr. Mena. What is the need for using fly ash? Does it really help in the damping process, or it's just a form of construction?
The use of fly ash is beneficial with the performance of the concrete. You get only by using this byproduct, you're reducing the amount of cement in the mix. So you're reducing the water cement ratio. You're reducing the heat of hydration, which is it's important when we're dealing with the mass concrete. So those are the advantages, basically.
So-
They are not related to the damping.
Now, how do you manage to transport that? You didn't probably have a plant at the site.
No.
So you
New
transported
York
it.
City is different. We have different plants outside the Manhattan borough. They'll be in Brooklyn, some in New Jersey, and they just drive into the city.
Right. So then the retarders or the admixtures that you added to it, did it affect the concrete, the process of it? Or what kind of retarders you use?
They have they have limitations to what they can add at the site, like super plasticizers. But everything else is done in the plant and is delivered to the site. It's we're talking about anywhere between 30 minutes to 90 minutes.
Yeah. I have some questions for John. Can I ask what's the phase for this project? Have you determined which option you're going to choose, and have you passed the expert approval?
Yeah, we passed the expert panel approval last year, and the scheme that actually was accepted by the experts was the BRB scheme.
Okay.
And I think that the Samsung has actually broken ground in February 2014. So.
Okay. Could you shed some lights on the say the cost impact of these three different options? Basically, you said
Yeah.
structurally you think the viscous damper is the most efficient, right? But how about the cost? And also the other question I have is you mentioned you said the regular outrigger is not very efficient because of various reasons, and one of the reasons they cannot dissipate any energy. And you said you sized the outrigger to not yield even under severe earthquake. I'm wondering, like, whether this is your decision or it's somebody else's requirement, because my understanding is that you can design the outrigger to yield under severe earthquake.
Yeah, I mean, the outrigger system is very efficient. But the concern with an outrigger system is always the design at the panel zone. And utilizing embedded steel is a way around that. And we just, from our past experience, trying to get work approved, we knew that these strengthened zones were actually zones where a lot of design work was actually required. And one of the options is, in this case, we had a client who was willing to investigate utilizing newer technology. And it was not necessarily, we didn't go into this study with any preconceived ideas about one system being more efficient than the other. We knew that there was kind of a drawback at some point where you would diminish the returns on using something that was actually going to reduce the stiffness. But we wanted to just see the range of the answers. So like the outrigger system, it's a very efficient system. There were some demands that were put upon us. I don't believe that in the final approval that even in our initial studies that they were demanding that the outriggers stayed elastic if we were utilizing a system like that. We were just looking, and in this case, we were looking at just a comparative study. So it was a little bit different than something that you would actually try to take through a full approval with experts. I think that the experts did have a concern about utilizing dampers for the frequent level earthquakes and for also the design wind levels. And as a result, this was kind of a compromise to utilize a BRB system.
And as I suppose also finite element analysis of all the building.
Yep.
I'm wondering how big the differences in the results was. And the second question, when is exactly the moment when you put the dampers into the building? After the wall get the full strength or after all the construction works are ended?
Yeah, I'll field the second part, and then Mike could probably speak to the time history comparison. Essentially, what's going to drive this, because it's in downtown Toronto, analytically, it's not too fussy in terms of installation time. We sort of intentionally left these things modular just because, they're not exactly, they're a robust device, but, you don't want to sort of leave them kicking around on the construction site. So essentially, we've spec'd a temperature installation range because we want to ensure that the VE material is not embrittled. So likely, these things can be installed kind of at any point once the trades are out of the way. It'll really depend on what level they hit in the winter. So likely what will end up happening is the VCDs will go in after the skin is up past these levels to a certain degree, and there is some amount of climate control in the building. And that's just one sort of constraint that we've had to work through with the owner and the construction manager. And then I guess, Mike, you've sort of looked at the comparative results of the time histories with RWDI.
Yeah, so they conducted a pressure test, so we had multiple kind of wind tunnel time histories up the height of the building. And then what we did is we looked at the response under, a number of different angles of attack. And in general, under the dynamic loading, it reduces kind of as a percentage of your damping that you actually have. So in general, the results that we showed there, say 30% decrease in acceleration would hold for most of the dynamic motion. Now in the actual static kind of contribution to the wind load, the dampers have not any effect effectively. They don't reduce the response there. But for any dynamic load, the dampers are quite beneficial.
My question would relate exactly to the end of your presentation. If there's a difference in the periods, for example, between Beijing and Shanghai. So did you see some regional results?
In Beijing, it's mostly seismic controlled design, and in Shanghai maybe a wind controlled design. And but we have some other regulations, not only on the story drift, but on the stability, like so we try to find the differences from a different zone. But for the super high rise, we have very small numbers. But you can find in Beijing we have the Z15, we call the Zhongguozun, I don't know, more than 500 meters high. And in Shanghai we have Shanghai Center. They have similar relationships because not only we not only control the story drift, but the stability or other things. But in general, structures in Beijing will be stiffer than Shanghai.
Right. Thank you.
I'd like to add to that one. Obviously, looking at Shanghai and the drift requirement, in particular for wind load, essentially you have the strict in the drifting criteria, especially for H over 1,000, for example, for concrete buildings. Essentially that by itself put a huge limit in terms of the stiffness of the building, what you need to accomplish. And by doing this is automatically actually limit you in terms of the building period and frequency. And that's what we had, for example, when we designed Jimao. Initially we had to meet H over 1,000 drift, which means that at the time we could not really use the Chinese code to meet the H over 1,000. So we went into more rational way of approaching the project, in which we use the wind tunnel to achieve H over 1,000. But for the building using the Chinese code, we were able to achieve H over 576. So by doing this, essentially you made the building much stiffer than it needed to be. I think the building period for Jimma is about 6 seconds. The torsional period is about 2.5 seconds. It's very torsionally very stiff. Now, if you go to Beijing, the criteria, as he mentioned, is more strict by seismic, regardless of the height. So the phase shear is absolutely huge. And at the same time, there is a certain performance criteria that you have to meet in order to limit, to achieve that. You have, again, to make the building very, very stiff, related to inertial drift and others. So regardless of how you look at it, you make the building much stiffer than you need per international standard. And between the two, obviously, that's the reason he has a much stiffer building than we typically do in Western, ASCE, in the U.S., North America, or Europe, or other building codes.
The winter and summer in Korea, the amplitude of the temperatures reaches, I don't know, 60 degrees. So how was the response of the damper, and how big the damper was? It was from the sky bridge to how many floors higher on the tower it was mounted? Thank you.
The damper is multi-stories, about 4 floors. And at the same time, we are not using it really for strength. Part of the reason, because the building, as you can see, several buildings stacked up on top of each other. So as you would think in the moment frame, think of this building as simplistically as a really mega frame system, essentially. And I'm just adding a damper at this to maximize the amount of deformation that happened in the damper. So the damper is fully used not for strength, but mostly for reducing the dynamic response of the building and adding damping. And based on our analysis, we were able to achieve more than 6% damping out of that system by itself. Again, this has not been tested. Again, it's just additional studies that I've done, which is above and beyond what the architect wanted to do. And in fact, when I look at the building, visually, the original system looked very static. By adding these elements, I think it just added a little bit more dynamics to the building, and actually it enhanced its overall visual. But at the same time, in terms of, we use tailored devices. We don't need the very large damper because essentially we're using them only for just supplemental damping. Okay. Again, we looked at other options, to enhance the dynamic response of the building, but this one, I thought this was the most effective way of dealing with that. And I think if you look at mega outrigger system, there is no reason why you can't use that. I think it's almost, with the outrigger system, it's a mega frame system. It just happened people call it outrigger, but it's really a simple mortal frame.
We have been monitoring buildings all around the world, but our experience is that for steel building, with a good finite element model, we can match the time period or whatever we have very well. But the trouble is with concrete buildings. We have recently done a damper design for a building for 6 seconds. Everything is done, and when we go to the building after it's built, it's showing 4 seconds. That's nice. So do you have any database which would help? Because most of the designers would have more difficulty in coming up with the right period, even if they're using their finite element code for concrete buildings. Maybe Ahmad can
I think it's a good question, and I think we have some data for the real period of structure, but it was gathered about 20 or 30 years ago, so only for the lower structures. But I think for these super high-rise buildings, and they have TMD systems, they have to tune the mass. I don't think they will have that big gap from 600 to the 6,000 to 4,000, 6 seconds to 4,000 seconds. But I think concrete structure is really a big problem because they can stand very small deformation. If for a larger deformation, they will have cracks or something that the owners don't want. So we have some study on using of high strength concrete because we have some limitations in China to use high strength concrete because they may have very poor ductility, but I think they have higher strength and higher deformation ability. So I think it's a good way to use high strength concrete with a damping system. I think it's maybe it's a direction in China for super high-rise building.
I think as a follow-up to that, I mean, the point raised here is the initial period, which is one question, but there's also the variation and change over the life of the structure. If you go from an uncracked concrete structure and you go all the way to ULS cracking, you can see variations of as much as 50% on the period. So I think the question is, have you monitored any buildings for a longer period of time and related it with the loads that have been applied to the structure?
I didn't get the data, but I think we have some in China.
Okay. Any other questions?
I'd like to add
Yeah, go ahead.
to that. I think, as you can see, there is a very large spread in data. And to calculate the period is very much function of what structural system you have. There are some buildings and some elements that not necessarily accounted for in the design that could add a significant stiffness. And sometimes, believe it or not, non-structural component, especially in a concrete building, can contribute a lot. But again, if buildings are very predictable and have a very well-defined structural concept, and you have a very good analysis model that incorporate most of the key issues and modeling techniques is good, you will be able to match it. For example, Mr. Hassan Karim and myself, we've been watching Burj Khalifa for the last 8 years almost. And essentially we match the fundamental periods within 2 seconds, including the higher modes, up to 12 modes, as you can see from the charts that I showed you. Again, how well you define the structural concept is very important. When you go to tall buildings, generally they tend to be more in the elastic range, but where the diversity happens in more residential building, concrete building, participation of non-structural component, partition, the cladding system, and the magnitude, what has the building experienced. And these are the kind of things that tend to be a little bit more what it creates a widespread in data and concrete structures in particular.